Perfect. So hello everyone. So today we're excited to have Dr. Aure lien Stcherbinine, which is a postdoc. Yeah, okay, go ahead. So Aure lien is a postdoc at the Northern Arizona University since January 2022, and before that he did his PhD in France at the Institut d'Astrophysique Spatiale, where we actually were colleagues at that time. We did our PhD, not in the same team, but together. And so he did his PhD on studying like the Mars atmosphere and surface using Omega and SES probes. And today he'll be focusing more about his recent study on the water ice clouds in Mars atmosphere. And just a few reminders, this seminar will last something like between 30 and 45 minutes anyway. And please, if you have a question on Zoom, you can write them in the chat so that in the end you will just ask those questions if you want, or you can ask them yourself. And yeah, and the meeting has been recorded, as you all know now. So the floor is yours.
Okay, yeah, thank you, Leon. Okay, so hello everyone. From just tell you today, I'm going to tell you about Mars, and especially the Martian atmosphere and the Martian water as clouds. Mostly with the surveys we can use with the probe. I'm going talk a bit more about so the instrument atmospheric chemistry suite. So it's the work I've more to done in France in my previous lab, but I'm still doing it, still working at the NAU. So just a few words about the Martian landscape currently, but more studying Mars, because today it's an amazing time for studying Mars, because we never had that many probes. So the first time spacecraft fly across Mars was in 1965, D-5. It really changed how we understand Mars and the planetary science. And currently, we have more than 25 probes that reach Mars, including 10 probes that land on the surface, 6 rovers, and today we have 3 active rovers. So the 2 US one and the Chinese one, Durang, and we have 8 orbiters. So we never had that many probes looking at Mars, at both the surface, the atmosphere, and everything. So it's really an amazing time. We get a bunch of data coming. And so today we're not going to talk about the rovers. So yeah, that makes lots of nice pictures, but we're going to talk about the orbiters. What you use to do the atmospheric science. And so just a few words, because I guess we're not very familiar with these longitude. So on Mars, 1 Martian year is approximately 1.5 Earth year, but we don't have the equivalent to a month. So we divide Martian year into solar longitude, not an LSOBS. So basically start at the spring equinox. And 1 Martian year is 360 degrees of LSOBS. So I'm going to talk a lot about LSOBS, so it can appear in the figures. It just, where we are into the Martian year, just, the units of time for us. So, you may know that Mars currently, everyone is looking for water, especially, but we're talking about liquid water. So, but currently we don't have liquid water stable on the surface of Mars. It has been for the few million years before. We have evidence of the presence of stable liquid water. Currently, we don't have liquid water, but the water cycle is still a dynamical system, really active in Mars. So what do we have? We have the water vapor in the atmosphere. It's lots relative to Mars. It's mostly CO2, but we have some water vapor in the Martian atmosphere. This water vapor can condensate to form water ice clouds. So the clouds of Mars, it's only water ice clouds. So Mars looks like the cirrus that we have on Earth. It means that it's ice crystals. It's not water droplets. That most of clouds on Earth are water droplets, but on Mars it's only ice, because water droplets means liquid water, and liquid water is not stable. So it's gas or solid or ice. We can have some water, we say, adsorbed on the surface. So it's water molecule that are lightly bound to the surface molecule. So this one could be really extended between the surface and the atmosphere. You have ice also on the surface, either for the polar cap, really massive, or deposits, or in the subsurface, because it's permafrost, so a lot of ice under the surface, Mars. And we have water in the minerals, that it had hydrated minerals, and that's mostly how we know that in the past water has been stable on the surface of Mars to form these minerals, but some of them can still actively form today with the interaction with ice, because I said it's a dynamical system, and so lots of people are currently working to understand, okay, how does all this reservoir interact with them? How does the water, because if you want to understand Mars currently and to model it, to understand the weather, the evolution, and to understand the past, how does it evolve from climate that may have looked at Earth billion years ago to the present day Mars? We have to really understand how does everything move. As we see, we don't have liquid water, so all the interactions between the ice and the minerals is going to be through the water vapor and the water ice clouds. So yeah, only give you a few clouds about why it's interesting to look at water ice clouds. So also because it's nice, here you can see. So it's a picture of water ice clouds. Actually, they are taken by the Curiosity rover a few years ago, multiple Mercury. So I say clouds are really important to transport the water across the planet between the different reservoirs, between the ice, between the absorbed water. So we have the water vapor, but they don't have the same dynamics. You see here are maps of the water ice clouds in the atmosphere and the water vapor. So here with the y-axis, it's the latitude on the planet, and the x-axis, so it's the LSOS over 2 Martian years. So it's the seasons in the time. And so we can see that the region when we have lots of ice in the atmosphere, not necessarily the region when we have lots of water vapor. So it really has different dynamics to exchange and to move the water across Mars. So that's why we need to study also the water ice clouds. The presence of clouds means that we have crystals in the atmosphere in suspension that will affect the structure of the Martian atmosphere, because particles that will absorb and scatter the incoming sunlight. And so that's locally affect and change all this physical and thermal structure of the atmosphere. And although you know that Mars over its history has lost lots of its atmosphere and its water into the deep space. So we have the atmospheric escape. Because so basically it's the hydrogen escaping, but the water vapor can be dissociate into oxygen and the hydrogen can escape to Mars. But if water is condensated into water as crystals, it's harder to dissociate them and to make escape. So the presence of water as clouds locally can affect the ability of the atmosphere to escape into the deep space. So they're really important. So for decades first, water ice clouds have been neglected in the study of Mars. But for the last 20 years, people start to realize that if they really want to model to understand what happens, they need to include these water ice clouds. So that's what currently we need really more observation data to refine the models and to understand, because we discovered that their role can be detected pretty some of the major parts in the exchange in the groundwater cycle. So how to study them? Where did my ability I'm going to present you comes from? So my growth, I'm mostly using the middle infrared channel of the atmospheric chemistry suite instrument on board the ExoMars Trace Gas Orbiter probe. So it's collaboration between ESA and Roscosmos, starts operating in spring 2018. So it's one of the last probes that reaches Mars currently. And so the spacecraft is orbiting Mars. It's an orbiter. Approximately it takes about 2 hours to around Mars. And this instrument is dedicated to what we call solar occultation. Solar occultation means, it's in the schematic, so it's orbiting on Mars and is going to look at the sun. And when Mars goes between the sun and the spacecraft, it's going to look at this light of the sun transmitted through the atmosphere. And so it's orbiting, it's taking bunch spectra all the time. And so we can have lots of spectra at different altitude and get a profile of the atmospheric extension. So at the end, it takes also some spectra outside the atmosphere and you just compute some ratio between outside and inside, and you have easy access to the transmission really of the Martian atmosphere. And so all these component water, scalp water vapor, heavy gases are going to provide some signature in the infrared. So how do you use infrared spectra to study the Martian water ice clouds? Here you have some model of the extension of particles of ice crystals for different sizes. And you can see for each color is one size. You can see that we have this wide and broad feature around 3 micrometer, and it's really sensitive to the size of the particle. So it's all very indicative of the presence of water and water ice and the size. And so with ACS, we can get for 1 set of observation, one profile, spectra, different attitude, and look at this band. But just one thing, ACS has been designed to study the trace gas of the atmosphere, like methane and everything. And so it has very high spectral resolution, but smaller wavelength range, because yeah, it's a compromise between the resolution and the coverage. So for one shot for me, I cannot look at the entire free micrometer band. I have only half of it. But we can see that there is a lot of it. We can manage to get some information for that from the spectrum. So first, we're not going to use the transmission only, because we measure transmission integrated along the line of sight, so around lots of parts of the atmosphere. But we can use some onion peeling vertical inversion. This is the only equation you're going to see here if you don't like them. So it means that we're going to assume that the atmosphere is composed by homogeneous spherical shell, and we're going to convert this transmission integrated around all the line of sight into the extension and local properties of every shell. And so we just convert them, and instead of transmission spectra, we get extension spectra that tell us about the local property of the atmosphere and not mixing every attitude. So this is one spectra I can retrieve from ACS, and we compute model from the extension for water ice particles, different size. And we're going to try to fit this model with our data. So with that, we can have at the same time two information. Are we able to fit models to explain our data with water ice? Yes or no? And if some models can reproduce observations, which one? And so give us information about the size. You say, okay, this one between 0.5 and 0.7 micrometer if it's water ice. But have to know on Mars with another kind of aerosols particles. It's a Martian dust. Dust is small particles coming from the ground in the atmosphere. That's why the Martian atmosphere is orange and red, because it's just full of dust. Dust has kind of signature in the free micrometer region. And so to be sure that we're not talking about dust, that's ambiguous, we compute the exact same process for dust model. And if we have any ambiguity at all, maybe some dust, we say, okay, we remove, and in the following, we're going to focus on the rubber detection that can be explained only with water ice. If it's some ambiguity, no, let it go on the side. We want really strong ice detection, and so we have the presence of ice and the size of the crystals in the clouds. So we have this for same idea every time, lots of attitudes, and we can get vertical profiles. Can here move from the bottom to the top of the region of Mars with atmosphere when we have lots of aerosols and particles, and we can have this indication about where the cloud is and what is the size of the particle between the clouds as we get there. And so now we can start to do some science, not just processing. So first we can see about, okay, if we look individually about some vertical profiles, how do they evolve? So we can see that at higher altitudes, we observe the smallest particles. You see, the higher we get, smaller particles you're gonna go. It's observed for like individual profiles, but if you take lots of data, like this one, and the same thing is the size and the attitude, you can see that you can get this trend. If you get higher, you're gonna get smaller particles. So that's something expected from the models, because the higher you get, the less water you're gonna have found, so the harder it's gonna be to condensate large particles, and also just gravity. When you form larger particles, they're gonna be heavier. They're gonna tend to fall down a bit to the lower regions of the atmosphere. So that's it. So here we have just represented all this data we have over the last 2 Martian years, so 4 Earth years and Mars. So here we have also the time SOS and the latitude of observation. So just think, but every point is vertical profile. So it's 10, 20, 30 observation on spectra. So it's each profile. First, we're going to focus on the first model of operation of ACS. Because you see, you have this shaded region called GDS. So GDS means global dust storm. global storm are some incredible events that can happen on Mars that are really impressive. So local dust storm happens every year. You have lots of dust storm on Mars. But here, if you look, so it's vertical profile as the best, and when you get some color, it means that we detected water ice, and the color indicate the size of the crystals. And see that just this, we have really two different categories. See, two different regime around SOBS 200, and that corresponds to the beginning of the global storm from 2018. So when we talk about global storm, it's something that doesn't exist on Earth. It's not like global storm you're going to see in Sarah. We talk about global storm that's going to cover the entire surface of the planet for like 3 weeks, 1 month, maybe more. So during this time, you see, so it's picture take, you see, in May and July 2018. At this time, you can no longer see the surface of Mars, either from the orbits or from the ground. Everything is just covered. The atmosphere is full of dust. Everything is changed. So it's a major event. There occurs every 3-4 Martian years. We don't know lots about them. We cannot predict them. So yeah, that's a question. And this one, as we have lots of orbiters, we get lots of data about this one, and everyone wants to understand, okay, why do such events happen sometimes? One cannot be able to predict them, and what's the influence also of the on the clouds and the temperature on everything, because there are lots of things. So if you come back to our observations, we can see that first, during the global storm, we have normal increase of the typical high of the every clouds. You see they take about, the maximum altitude go increase by about 20 kilometers higher. You have lots of very small particles because we are really high that dominate. And also we observe this. So this is relatively large particles. So between 1.5 2 micrometer, but observed above 60 kilometer in height. That was not expected, but it's really high. It's pretty specific to see, okay, this global storm, it really raised like everything in the atmosphere at higher altitude than expected, that we've seen before. So so I mean, just get lucky because NCR just started operating 1 month before this global storm appears, and we can predict that. So we have this incredible data to look at the effects of such events. But ICI didn't stop, and it's still operating currently. We continue. Currently, it's really healthy. So we hope it will continue to get a lot of data, and also it provides us the opportunity to monitor also the evolution over several years, over the season of the Martian year, how do the clouds evolve. So we can see, especially, so here we have, have the alignment between Mars and the Sun, so we cannot get a lot of data, so that's why we have this kind of order. But here we have more than 1 full Martian year with a bunch of observation, like regularly we have this monitoring. So if you look at this, now we can have the seasonal evolution. We only focus here in the equatorial regions, and we can see that really around aphelion, so close to the summer in the northern hemisphere, clouds are higher, about average around 70 kilometers in height, but during winter, very same, so the period when Mars is farther away from the sun, average altitude of the clouds goes down to 40 kilometers. We have around 30 kilometers difference between the winter and summer for the altitude of the clouds. So everything just moving. So that's really interesting to see. So, but I told you that here I only select like the mid-equatorial and mid-latitudes. Don't look at the poles because because if we did the opposite thing, we select small range, the same period, here only spring, summer in the northern hemisphere, and we plot altitude versus the latitude this time, you're gonna see we have this bell shape, because in the polar regions, clouds are mostly observed between 0 and 40 kilometers, but if you go to the higher latitudes, to the equatorial latitudes, the clouds here are observed between 40 and 80 kilometers. So you have about 40 kilometers of difference between just the pole and the equator. So you have these two effects. With the season, everything's moving, but just take snapshot of Mars one time, and the atmosphere, you have this evolution there. you can see that, yeah, it's not really center. So it is slide. And we all still have around the equator, like everything, all the atmospheric structure is left higher. We all seeing these large particles, but they're only around 40 kilometers. So it's not the 60 kilometers that we observe during the global storm. So really shorted, but global storm is something specific. Something happened during this month of just everything moving, everything messing up. So yeah, but we have this information about the clouds, how do they move, and so something also important. We can see that the clouds usually they are almost at the top of our profiles. Means that the most of the dust and the vapor and everything is mostly captured a bit before. So that's, I was talking about the influence of dust on the atmospheric escape and everything. And so knowing where the clouds are, can also get profile of the water vapor, of all the other elements. So knowing precisely where the clouds are to compare after that to the other one, it's also something that we want to know to understand, okay, everything will move. So yeah, so I was preferably mostly talking about the general attitude of the clouds, but so if you look about the size of the crystals versus the altitude, so I saw before, but here it's a more precise view. We can see that, yeah, these smaller particles really goes to the higher altitude, get higher, get smaller. Here it's also very clear to see the effect of the global storm. And you can also see that the global storm doesn't affect the cloud in the same way everywhere on the planet. You see, like in equatorial latitudes, if you compare observation during the global storm, the red one, to observation during the next Martian year, approximately the same season, but you see that everything moved with the season. So we want to compare the same season to have everything, most of the parameters similar, just changing global storm or not global storm. Okay, don't have everything moving at the same time. See that it's approximately, yeah, between 10 and 20 kilometers higher during the global storm compared to a regular year. If you're looking in the polar regions, it is much more impressive. You see that we can go up to 40 kilometers of increase at the same period, same time, just the global storm. So the effect is much more important in this polar region where cloud expect to be low. And something else happened in the Martian year 35. So the next Martian year, we have a regional dust storm, because yeah, we have regional dust storm every year on Mars. We can say, okay, but is it something really comparable to this global dust storm? How this matches the global dust storm like stronger also on its effects on the clouds? So we can see that here, because this blue region shows the region of the global dust storm, but the regional dust storm happens in the northern hemisphere. So we can see here it's indeed increased to the altitude of the clouds, but only about 20 kilometers. So it's not these 40 kilometers seen in this polar region. So it's really sure that, yeah, this global dust storm, they are something massive, something huge. It's not just let's say a small regional dust storm. It's much more important event. And you can really see that here. You can also want to see, okay, but another information we can get is how thick are the clouds, because we're just talking about cloud transmission. So we have information about how thick they are. So because you say, okay, we have the size, but depending on how many particles you're going to get, it's going to be thicker and higher. And so yeah, something important. Finally, we can see that we have two different regimes for these smaller particles. We have like an increase of the thickness of the clouds when the size increases, but from particles larger than 1 micrometer, don't really see that strong evolution. So it's kind of similar. And still going back to this period with this dust storm, the global storm. So we say that the clouds are observed higher in the atmosphere than in the regular year. They are higher, but they are higher, and also with large particles sometimes, but they are fainter. So it means that they get these large particles higher than expected, but there are not that many particles compared to when we observe similar clouds, with similar size, lower than higher, bigger clouds, but still fainter because they are higher in the atmosphere. And so that's what you can really see with this ACS data. And so here we have all these observations, so the monitoring of the storm and the seasonal and latitudinal monitoring of the clouds and their properties. So what we can do is so I'll say that we need clouds, I mean, we need observation to fine-tune our model and to better understand how Mars is working. So what we can do is say, okay, now we have this new data set and this observational constraint. How do they compare with current model of the Martian atmosphere evolution? So we compare them to what we call general circulation model. So it's 3D simulation of the dynamic evolution of the atmosphere that includes all this, the gas, the aerosols, the interaction with the atmosphere. But it's but something. So I don't run VGCM, but work with people that run them because my work is not really simulation. And so almost for Mars currently we have maybe like 3 or 4 big GCM that exist. The UNH GCM, another one from the UK, maybe one other working with China, them, and although for Europe we have Western Europe, the one led by team, although with French, Spain did this. Before was the LMD GCM, now we call it the Mars PCM planetary climate model. So just one name for one of the GCM, because between this one that can have some tiny differences in the implementation or some microphysics is better represented in this one, but this other part. So but they are one of the most used GCM currently. And they have this wave interface called this Mars Climate Database, the MCD. They like to change, but just write like climate Mars something, and you mix the data, then you get lots of lots of different names. And so they as prediction, but they also already use some retrievals, like the dust distribution is something that the model are not able to model and to predict correctly. So and it's important also for the clouds. So what they do, they generate some predictions and models, but when they get the retrievals from all the orbiters about the dust distribution and everything, they include them in the model, then run again the model to get higher resolution and more resolved with observational input to have the model to run and to adjust. So that's what we use, and so that's why we only compare here with Martian year 35, so not the most recent data, because they don't have rerun the models with the observational data for the just more recent one. For clouds, it's really important to have the just purposes and distribution, so we don't really make sense to compare because we know it's wrong. And so here it's kind of small comparison. So still on so we have the Midlatitudes and the polar inversions. So on the left, it's our observation with ACS, with the presence of clouds. And on the right is where clouds, so water ice is expected in the atmosphere by the Mars PCM. We can see that indeed, this seasonal trend is kind of well expected and reproduced. Only difference we can observe is in the high. See there, you can go until up to like 70 kilometers maximum, where we observe clouds up to 80 kilometers. So we have about typically 10 kilometers of difference between when we observe them and when they are expected by the PCM. So about the lower bound, I would say that maybe I would say that if we have any ambiguous case, we will remove them for our retrievals. But at lower altitude, maybe we can have like a mix between dust and water ice that we will not detect because it's the limitation of our methods. But maybe lower here, for them, they don't care about if there's dust or they just say, okay, we predict that ice will be present. So the thing that clouds extend lower than us, we can say that, okay, it's just a limitation of our retrievals. But the fact that we see clouds higher than there, and they say, okay, there's nothing, no dust, no clouds, and everything, shows that, there's like something, small discrepancies between the models. So that just have to understand, okay, why don't I predict to go as high as it's observed? So in Midlatitude, but it's the same, similar trend also observed, like, for the more polar regions, CDPAR, clouds up to 80, 60, they will just stop at 60 kilometers. So, but overall, models are kind of incredibly, yeah, I mean, their works, like surprisingly really well, but we say, okay, but we can improve like fine tuning to make them even better with all these observations. Can also compare like individually with the profiles. So yeah, to just have a better look. So in red every time is the axial observation. So it can be the clouds detection, also in light blue. And here with the thickness of the cloud, because it's something that can be also predicted by the models. We can predict the thickness of the clouds. So we can see, but sometimes, yeah, you got kind of good agreements. But something especially which is not really well predicted and reproduced by the models is the case when we have second layers. Yeah, we call this detached layers, dust or clouds, and see that usually when we get that, model gets lost. Model predicts the first layers, but it don't predict the second layers to appear. And typically, yeah, usually models don't predict these second detached layers, and sometimes it just speeds slower. But works pretty well. Yeah, just to show you where it's working a lot. Okay, yeah, so you got some nice GIF made by, I guess all of them are the Curiosity rover, but yeah, Perseverance now make also observational clouds. So yeah, it's fun, it's nice. Yeah, so just to conclude briefly, so now with this ACS instrument and also some work with normal, we have long-term annual monitoring of the seasonal evolution and the latitudinal evolution of the atmospheric scale. So that's something really new to get this information about the vertical structure of the clouds, because it's not just looking like by above and say, okay, here there is some ice that is insulated. Here we have, for every time we have vertical profiles with the precise properties of the clouds. So this covers that's something really new provided by this slow rotation method instrument that we have on Mars like 4 years ago. We didn't touch observe the quasi-systematic presence, because even I mean in the figure all the profiles required by ACL are present, and in almost all of them clouds have been observed at least at the top of the profiles. And so let's say, okay, so at least at the morning and evening where we can observe like with this slow rotation, clouds are almost always present in the atmosphere. So that's the kind of result. We can really measure and characterize the amplitude of the variation of the high by the season and the best, and we can compare with current models and to compare and to try to help them to improve the model. Yeah, I mean, although the size of particles, I mean, don't show it here, but we have like stronger discrepancies between the for the size predicted by the models and what we observe, and also what all the team observe with their instruments. So there's something that should be currently people from the PCM, we are talking like last June, they are working to understand why the models predict particles that can be sometimes up to 10 times larger than what is observed by all the spacecraft. So yeah, I mean, and so that's something, but we don't have. I mean, we're just starting to get lots of data about the water clouds, because before that, we're not designed to do that, because clouds were neglected. So we have a lot to do to really understand the clouds and to help people to better model them and to include them in the model. So yeah, we have a few publications about this. And just before ending, a few words about the next project I'm also working on. It's with this new probes, the Emirates Mars mission that's around Mars last year, 2021, as the was launched at the same time as the Perseverance rover with 3 missions going to Mars. And so it's really a collaboration between the United Emirates and the US. And yeah, lots of most of the instruments are US led, and what you can do. So it's also an orbiter. So I don't do slow rotation, but I'm also working with some people with we call the EXI instrument. So it's through this imager. So and he can retrieve the vertically integrated optical depth of the cloud. So we don't have this vertical profiles of the properties, but we can see where the clouds are. And as it's through this, we have snapshot of Mars as over the day where the clouds were distributed so what we try to do is to make some cost comparison, because here we have a global coverage, lots of physical information. With ACS, punctual information, but all the properties we want about the clouds. So say, okay, and both probes are currently orbiting Mars. They are currently acquiring data, so we are looking for close observation. We can have this side and locally all the information we want from ACS, and try to see if we can do something to extrapolate and to try to better understand the global behavior of the clouds. So thank you for your attention.
Great, thank you. That was a great talk.
Yeah.
Does anyone have any questions? Yes, sorry.
That's a nice one. And if you go back to the previous slide, what kind of temporal resolution you can have, like how often can you get those maps?
This one?
Oh, yeah.
Let's think about the EXI. You can get 7 maps per day sometimes, because I mean, it depends, because also work, several, I mean, it's several features, because if you imagine they use one specific feature to map the water ice. I mean, after that, it's also matter between the instruments and the data transmission something. But when they want, they can have several, at least 1 per day, or maybe sometimes, high resolution, high cadence, to several per day if they really want to get lots of monitoring. But EXI provide lots of image, because they also use this image sometimes to provide, like with the multiple band, like color image and beautiful picture of Mars. So they like to use this camera.
Another question. So you said, just to be sure, like ACS was the first probe with solar occultation measurements? In the
infrared, because before that, other solar and stellar occultation was the SPECAM for Mars and also SPECAL for Venus instruments. So also on the Mars Express probe, so Mars Express started in 2004. Also ESA mission. And this one was also solar and stellar occultation, but in the UV, not infrared. So ACS. So it's on the Gas orbiter, we have ACS and another instrument, Nomad, led by a Belgian team. Both of them are kind of similar instruments. We are also working with the Nomad team. But this one, they are the first 2, and currently the only 2 instruments working with solar occultation around Mars in the infrared.
Okay. Thank you.
Do you have any other questions? Can you see a hand raised?
I have a more naive question.
Yeah.
I'm wondering if the solar wind can heat or ionize the atmosphere, and if so, if there's any correlation between more global conditions and the patterns that you see in the weather.
Exactly. We want to talk about that before. We will not see, but if there's something with the clouds, because haven't been really investigated. But about the atmospheric escape and the water vapor, definitely, some papers are try to just study if there is some correlation, everything, but especially with major events, they're gonna have for short time, they're gonna increase the escape rates. It's linked.
Thank you.
It's gonna fight. Who wants to go first?
I got more. So we got sunlight and more focusing more on the visible part, and we have this ice cloud, right? Especially like upper part, you mentioned the particles get finer, right? The particles get smaller, like as you go higher up. Is it possible to see a rainbow? Like
Rainbows
that
on
you can
Mars.
perfect geometry.
I think with I know with with
Like,
then if you get enough density for the ice crystal. I had to think about it because I mean, and if can this water ice crystal mid dense enough to maybe I see that's atmosphere although lots of dust. So I mean these clouds, even clouds are I mean every time I show what it it's relatively to Mars, it's a lot of ice compared to what we get on Earth. It's really faint. I mean because just to think, let's see. Martian pressure it's 6 millibar. So yeah, I mean, compared to what we get on Earth to get everything, it's nothing. So I'm not sure we have really enough to make something that we can really observe. I mean, at least no rover has made a picture of rainbow because if they made, we're gonna see it everywhere. Rainbow on Mars. I mean, they observe the clouds. I don't know if in theory it's impossible, but in practice we haven't seen it, but maybe in theory, yeah, interesting. Should be nice.
I think the question's gonna get more naive, but I'm a layman, so I'm not in space by myself. So first of all, I'm not sure about the interaction between outer space and the exosphere of a planet and how water or is escaping from that. But can this kind of studies reveal kind of like the history of Mars in a way? Like, can you kind of like reverse trends and see how water kind of was on Mars? Much.
Yeah, so I mean so we know that I mean to estimate all the quantity of water we had in the past on Mars, and I mean especially to know if water has been like liquid and stable is mostly looking about the geology and the minerals and everything. But I mean how they can know that what Mars had lost its water is I mean also not my work but TGO and ACS did a lot of work on that. It's measuring because the D/H ratio, the deuterium over hydrogen, and that's also something we use for the like comets like Earth and water. So we say like, okay, initially we have this ratio in the proto solar system of deuterium and hydrogen. It's not supposed to change, but the hydrogen is lighter, so the hydrogen escape more easily than deuterium. And so they measure, and so ACS provide for the first time vertical profile of D/H ratio. So I mean that makes like the first one the science, nature, and everything. And so measuring the ratio compared to what we have on Earth, what we have in all the places of the solar system, we say, okay, initially we should have this ratio. It's much higher, so we have much more deuterium than expected. So it means that that quantity of hydrogen has escaped, has been lost from Mars. And so that's mostly how you can really quantify the amount of water of hydrogen, so water that has been lost.
Thank you, sir.
Any other questions, Nick?
So it makes sense to me why at like LS of like 270 around perihelion you would have higher altitude clouds, but I don't really understand why you would expect to see higher altitude clouds at the polar regions. Is it a temperature thing or is there something?
Yeah, you have something with temperature. I mean, so see that, so yeah, temperature. So clouds are, I mean, although like related to the freezing point. I mean, yeah, just think about the appearance. So we have as a gas dimension. So that's not enough because on Mars, you can have water in the super saturated state. So that's, I mean, just considering the freezing point, it's not really enough. I mean, it's a bit more complicated. So that's why we need observations. But yeah, it's related to the temperature and pressure and everything. So that's why, I mean, this bell shape that we can observe. It's there. It's here, you see, I mean, lots of the atmospheric structure is followed by this trend, the scale and everything. But about the fact that we have this seasonal evolution. Just going to show that, yeah. So something I have to know is for Earth, the orbit is a bit elliptic, but kind of circular, and so we have a bit of a symmetry, and this orbit is for us is mostly due to the inclination. Mars is much more elliptic orbit, and so it's different between being close and further away. I mean, so we have the inclination, the signal between the northern and summer and southern hemisphere, but like we also have this strong seasonal evolution due to the distance between Mars and the Sun, because it has a stronger impact. So typically the storm observed close to the here in the period. Some people like to talk about the storm season ranging from 200 to there, but I don't really not a big fan, because although some studies say but sometimes we observe the storm starting there, sometimes it can be storm there, so it's the end, it's beginning, it's a bit after. So I'm saying it's really wide actually, and sometimes you even have small thunderstorm periods and no spots. So the storm season, that was really, I mean, some people like it at a few times 10 years ago. Now people are more say okay, it's not really, I mean, it's maybe a bit too easy to say that okay, I mean, it's similarly, but the habitable zone, people say okay, it's nice to have general idea, but actually it's not that easy. We have kind of stronger symmetry for this season, and so also the temperature and the atmosphere and everything due to the symmetry, elasticity of the Martian orbit.
Great. Any final questions? I'm sort of got my eye on the chat, but I can't see any questions in the chat. Is anyone online got any questions?
Question in the chat. During Martian opposition, we see white clouds both in North Polar Cap is better way for Earth. Likely to mean water ice, so so indeed on Mars, we don't have only water ice clouds. We also have CO2 ice clouds. We also have CO2 ice on the ground. The temperature goes much lower, and so low enough to condensate the CO2 of the atmosphere. And instead, the Martian atmosphere is more than 95% of CO2. And actually, just fun fact, the overall pressure of the Martian atmosphere varies during northern and summer, because during the southern winter, large quantity of CO2 from the atmosphere condensate to the water scalp, and so the overall pressure can run 6 millibars on average. It can go to 5 to 7, 8 millibars depending on the season, because the atmospheric CO2 condensate in the polar cap and then it's going to be released, and it really affects significantly the pressure of the planet.
There's a second question from Chuck. So are there estimates for neutral escape rates from Mars?
I mean, I'm not really a specialist, so say about this escape. I mean, I won't know more about that, but I don't have in mind anything.
Oh, that was the second question, that wasn't mine.
Yeah.
Okay, so thank you. Okay, great. Well, I think we should thank our speaker again. Stop the recording now. So thank you everyone online for joining, and thank you everyone in the room too. I think we'll hang around for a little bit longer to eat snacks and also answer any more questions you may have.
Feel free.
Thanks everyone.
Thanks, Emma.
Thanks, guys.